Hello guys, today we're going to start a new unit on functions. And in this video, we're going to first learn how to write functions in R. Writing functions represents the key step of the transition from a mere user to a developer who creates new functionality for R. To illustrate needs for user-defined functions, let's consider a long approval example. Suppose the information a bank maintains about its customers is displayed in this table, where each customer is described in terms of these four characteristics. To decide whether or not to offer a customer a loan, the bank applies the rules described by a decision tree, which collects tests on different customer characteristics and leads to different loan approval decisions. With if-else statements at our disposal, we can express paths that lead to different decision nodes in terms of a series of if tests, as shown by this chunk of our code. Then we can run this code to decide whether a customer, say Amy, should be granted a loan or not. And this is a final decision based on our decision rules. And if we want to make a decision for a different customer, say Sam, we can copy and paste this block of code. Then change every Amy in this block to Sam and rerun this code. But there will be a chance of making incidental mistakes, as typing invites typos. Or you could fail to identify all Amy's that need to be replaced. Moreover, it could be hard for you to spot the mistake once it happens. Whenever we've copied and pasted a block of code more than twice, we should consider writing a function. And functions allow us to automate common tasks in more powerful and general way than copy and pasting. As data structures tie related values, functions bundle related expressions so as to run them repeatedly, possibly under varying conditions. So far, we've seen many examples of us built-in functions. So now you should have acquired an intuitive understanding of what a function is. In programming, a function is a machine that takes some input, called the arguments, does something with that input, and in many cases, returns output, called a return value. Most of the computations carried out in R involve the evaluation of functions. And because R is primarily a functional programming language, its style of problem solving is centered on functions and provides many tools for creations and manipulations of functions. In addition to R's rich collection of built-in functions and enormous functions provided by and-on packages, we can also create our customer functions when we have certain tasks that need to be repeated over and over. In R, we use the keyword function to introduce a function definition. The function keyword is immediately followed by a pair of parentheses, which encloses a list of parameters. Function parameters are a special kind of variables. They are used to refer to R objects provided as input to the function every time we run it. A parameter can take a variety of forms. For example, it can be a symbol expression pair, or a special parameter denoted by this ellipsis notation. We'll elaborate on the use of different forms of parameters shortly. The expressions we want to run repeatedly is grouped by curly braces, and is referred to as the function body. For example, here we want to repeatedly perform some operations on arguments referred to by x1, x2, and perhaps many more. Create some intermediate variables called y1, y2, and perhaps many others. And then we may do something more with these intermediate R objects. But typing down these expressions in a function definition won't make them run or execute. The function body will not be executed until the function is called. If the last expression in the function body is not an assignment statement, the R object it outputs will implicitly become the return value of the function. We can also use a return function to specify the return value explicitly. This return function can be inserted into any place in the function body. It can also have multiple occurrences. Evaluating a function definition results in a function object. And a function definition can be further wrapped in an assignment to give the resulting function object a name. Generally, a function is assigned a name, but this is not necessary. If a function is not given a name, it is referred to as an anonymous function in R. Anonymous functions are most frequently used as arguments to other functions, and we will discuss them later. After knowing how to define a custom function in R, let's try to rewrite the code that makes low approval decisions into a function. To do so, we simply copy and paste the if statement code and identify what we want to vary across different runs of it. In this example, what we want to vary is the R object indexed in these conditions. So we need to replace all occurrences of Amy with a function parameter so that we can use a single name to reference different objects. Here I replace all Amy's with customer. Remember to declare the name you use in the parameter list to make it work. Another change I made here is to change all print functions to return functions. So instead of printing decisions directly in the function body, this approve low function returns decisions as output. And note that once return is met, the function execution terminates immediately. Here I would like to make a comment on naming of functions. As functions do things, you should always choose a function name which explains as simply and accurately as possible what the function does. This will usually be a verb or some phrase containing a verb. Once a function is defined, we can get it to work. Note that typing the function name alone won't make the function run. Rather, R simply returns a string representation of the resulting function object, including the information about its body and environment. Function environments are not something you need to understand deeply when you first start writing functions. In R, the environment controls how R finds the value associated with a name. It is a bit like Python's concept of namespaces. Because environments are crucial to our understanding of how functions work, we'll delve into the details in the second half of this unit. To run expressions in the body of a function, or to call or invoke a function, we should append a pair of parentheses to its name and supply a list of arguments that match its parameters. Here we call this approve low function twice, with different inputs. In each call, the argument is bound to the customer parameter so as to be operated by expressions in the body to output a specific loan approval decision. Here, I would like to introduce two convenience functions. We can use them to inspect the parameters and the body of a function individually. A function should be called with arguments, or in simple terms, function inputs. Behind the scene, arguments need to be matched with parameters so as to be referred to in the function body when it runs. In R, function arguments can be matched positionally or by name. Positional matching just means that R assigns the first argument to the first parameter, the second argument to the second parameter, and so on. Here I would like to use this SD function, which is a built-in function that computes the empirical standard deviation of a vector of numbers, to illustrate different argument matching schemes used by R. Applying the structure function to it outputs its parameter list. Note that this function contains two parameters. One is x, which expects a vector of numbers, and the other is this NA period RM, which takes the keyword value pair form. When used in a function definition, this form is used to associate a parameter with a default value. In this case, false. If you use this form to specify any parameter to have a default value, then you don't have to specify the argument to that parameter at the point of call, because it can instead use its default value. This relieves us from having to specify the argument for a parameter every single time the function is called. So this NA period RM parameter has a default value false, which means by default, the function won't remove missing values when calculating the standard deviation. Then it's your obligation to ensure that there are no missing values in the argument for x. But if you cannot ensure that, you can simply pass a true value to this parameter to switch on the removal of missing values when you call this function. To see the effect of argument matching, let's first create a numerical vector for parameter x using this random number generator function. It draws 20 random numbers from the standard normal distribution, and the output is like this. In the first example, I rely on positional matching. Then, my data is matched to the first parameter, which is x. And in the second example, I depend on matching by name. Here, I use this familiar form to name this argument referred to by my data. Actually, the role of equal sign in a function call is different from that in a function definition. In a function definition, it is used to define a default value for a parameter, while in this case, it is used to name arguments so as to match them with parameters. When specify the arguments by name, it doesn't matter in what order we specify them. In the example below, we specify the NA period RM first, followed by x, even though x is the first parameter defined in the function definition. R also supports matching by partial name. As you can see in this example, R will match this false value to the NA.RM parameter, even if it is named with a partial name. You may also wonder, what would happen if we mix positional matching with matching by name? In such a circumstance, arguments are matched first by exact name, then by partial or prefix matching. And finally, the remaining unnamed arguments are matched by position in the order that they are listed in the function definition. Here, the myData object is assigned to the x parameter because it's the only thing not yet specified in this function call. In addition to just constant values, default values in R can be defined in terms of other parameters. Let's define a function that takes a vector of numbers and outputs a normalized vector with mean being subtracted and standard deviation divided. Because we want to accommodate some special implementations for mean and standard deviation, for example, the trimmed mean, we specify them as part of function parameters so as to take varying inputs across different calls. And the default values defined for the parameters m and s are the regular mean and regular standard deviation of the first parameter. And this example shows it works. This vector of numbers matches the parameter x, and its mean and standard deviation are calculated accordingly and used as the default values for the parameters m and s. And the calculation performed by the function body makes the passed-in vector normalized, as you can verify by looking at this result. However, if the passed-in vector contains an ill-defined value, all other elements will be contaminated in the output. As we saw on the last slide, the SD function has an option for handling missing values. So does the min function. So this function definition hasn't explored the full potential of these two built-in functions. The solution is simply to include a new parameter to control the na.rm option in these two functions. And the new parameter we introduce is y, which is specified to have a default value false. The resulting parameter list may look weird at the first glance, but it is indeed nothing but another application of defining default values in terms of other parameters. When calling this new version, this vector matches x by position, and this logical value matches y by name. And m and s use their default values. And this works. This ill-defined value no longer contaminates the remaining values. But the drawback of defining default values in this way is that the syntax is a little clunky. Next, we are going to introduce a special parameter, which allows us to rewrite the parameter list into a more compact form. R provides a special parameter, denoted by the ellipsis, that can capture a variable number of arguments that have no matched parameters in the current parameter list, and pass these arguments to other inside functions that may anticipate them. So we can substitute this special notation for the y parameter in the previous example, and also include this notation in adding function call as the placeholder for these arguments. So all arguments that have no matched parameters in the current function will be captured by this special parameter and then passed into the inner functions that have this placeholder. In this example, since this named argument does not match any of the parameters, it is taken by this ellipsis and further passed into these two functions to match their na.rm parameters. Since this special parameter is able to take a variable number of arguments, you will also see this notation in functions whose number of arguments cannot be known in advance. Examples of these functions include the C function for creating vectors and the paste function for combining strings. Because this is the first time the paste function is introduced, here I give you one example to illustrate how we can use the paste function to combine multiple strings. And because this special parameter is used in its definition, we can pass an arbitrary number of strings into this paste function. And this keyword specifies the separator used between any pair of adjacent strings. In closing remarks for this video, I would like to introduce a helpful slogan that could deepen your understanding of the role of R functions. That is, everything that happens in R is a function call. In simpler terms, all work in R is done by functions. This includes infix operators like addition, control flow keywords like for, if, and while, subsetting operators like single brackets and $sign, and even the curly brace. Each of these things can be written as a function, as shown by code examples in the right-hand side code chunks. Behind the scene, they are actually passed into calls to the corresponding functions. In practice, we would probably never write these operations or statements as function calls, because these infix operators, control flow statements, assignments, indexing operators, and curly braces are much more intuitive and much easier to read. However, it is helpful to know that every operation in R is a function, as it implies that we can overwrite just about everything in R.